Let me introduce myself. I'm Vitaly Uzakov. Let me start by saying a few words about my background. My professional interests include issues of thermal reliability of nuclear reactors. I apologize in advance for the machine translation and voice acting, but I really hope that the general meaning of my message will still be clear to you. In this presentation, I will tell you about one of the possible directions for the development of nuclear energy, the purpose of which is to improve safety and make the most of the energy potential of uranium fuel. This presentation can be considered a development of the concept of the Breastad 300 experimental demonstration reactor, aimed at preventing accidents at nuclear power plants that require evacuation, and even more so, the resettlement of the population. Therefore, I will first dwell on the main provisions that are laid down in the considered concept of the safety of a nuclear reactor, including the Brest reactor. Brest is a Russian project of fast neutron reactors with a lead coolant, a double-circuit heat removal scheme to the turbine and supercritical steam parameters. The project is being implemented in the form of the construction of a demonstration complex, consisting of plants for spent fuel processing and fuel fabrication in a closed fuel cycle, and an experimental reactor Breastad 300. The essence of the concept of a closed cycle of nuclear fuel use is the conversion of the uranium-238 isotope, which is not capable of a nuclear chain reaction, into the plutonium-239 isotope, suitable for a nuclear chain reaction. This is done by irradiating uranium-238 with neutrons in a nuclear reactor according to the scheme shown. Part of the produced plutonium can be spent in the same fuel campaign in which it was produced. Some remains in the spent nuclear fuel and can be chemically separated from it for use in fresh nuclear fuel. However, expanded breeding of nuclear fuel, when the amount of plutonium-239 produced is greater than the amount of uranium-235 consumed, can only be obtained in reactors with a fast neutron spectrum. Such a spectrum can be obtained using a liquid metal coolant, such as sodium and lead. From the point of view of safety, Breastad 300 will have a number of significant advantages over any reactor in operation today. It will automatically shut down when any parameters deviate. Technologically convenient as a coolant, sodium turned out to be too dangerous due to its chemical activity, which led to a high risk of explosions. Therefore, such reactors are not widely used, and in the design of the Brest reactor, lead was chosen, which is a non-combustible, high-boiling, and low-activation coolant. The high temperature of the lead coolant makes it possible to organize simple and reliable heat removal from the primary circuit directly to atmospheric air during emergency cooldown. The possibility of burning minor actinides makes it possible to partially solve the problem of the accumulation of one of the most dangerous types of radioactive waste, which has been dangerous for many centuries. The combination of the properties of heavy lead coolant and dense heat-conducting nitride fuel creates the conditions for achieving complete reproduction of fissile nuclides in the core and stabilization of the breeding properties of the reactor, which makes it possible to operate with a low and stable reactivity margin, to exclude accidents with uncontrolled power growth, fuel destruction and radioactivity release. Double-loop design with steam superheating ensures simplicity of NPP design and high efficiency. The absence of shut-off valves in the primary circuit reduces the number of possible failures, which makes the reactor safer. However, the Brest reactor cannot operate without circulation pumps, the operating conditions of which are extremely difficult, which is a weakness of this concept. To ensure increased safety and economic efficiency of low-power nuclear power reactors, it is proposed to consider the unusual design of a nuclear power plant, the reactor in which is located deep underground. In the proposed NPP concept with a thermal power of 135 MW and an electrical power of 55 MW, the circulation of the lead coolant is provided by natural convection, due to the difference in lead densities in the ascending and descending flows of the circulation circuit, which makes it possible to avoid the presence of moving mechanical parts under heavy load. The density of the lead melt at a temperature of 540 degrees is 10,568 kilograms per cubic meter, and at a temperature of 420 degrees, respectively, 10,424 kilograms per cubic meter. A significant difference in lead densities of 144 kilograms per cubic meter and a large circulation loop height of 56 meters make it possible to provide an acceptable flow rate in the primary circuit for removing 134 megawatt of thermal power from the core. Of course, this is much less than 700 megawatt, as in the breast reactor, but even this has its advantages, since the length of the nuclear fuel campaign increases many times over. Accordingly, the installed capacity utilization factor increases, which is defined as the ratio of the energy actually generated at the nuclear power plant over a certain period of time to the energy that could be generated with the continuous operation of the nuclear power plant at the design capacity for this period. Thus, with the utmost simplicity of the primary circuit design, passive heat removal from the core is ensured according to the principle of natural circulation, not only in the cooling mode, but also in the normal operation mode. The design of the circulation loop under consideration has the properties of internal self-protection, since the possibilities of negatively affecting the operation of the reactor in case of erroneous or malicious actions of personnel are limited. There are several other important points regarding the location of the reactor deep underground. First, it is the relatively low cost of decommissioning such a reactor. Huge funds currently spent for these purposes reduce the competitiveness of nuclear energy. An example is the decommissioning of a nuclear power plant in Lithuania. Secondly, it is the provision of simple and reliable physical protection of the facility and the minimum risk of a terrorist threat for such an facility, as well as the minimum impact on the operation of the reactor of adverse external influences, aircraft crash, hurricanes, earthquakes, explosions during man-made accidents at nearby facilities, etc. The simplicity of the NPP design and the duration of the nuclear fuel campaign make it possible to ensure the safe operation of the reactor plant with a minimum number of operational and maintenance personnel. The qualification requirements for personnel may be lower than at current nuclear power plants with their complex and branch systems. Normal heat removal from the core, even when the reactor is operating at power, is ensured regardless of the availability of power supply, since there are no circulation pumps with electric drives. And one more important circumstance concerning the simplicity of the design of the reactor plant: the absence of complex and expensive elements, such as circulation pumps and shut-off valves, allows not only to reduce the cost, but also, ideally, to ensure the mass production of reactor plants. So, let's take a closer look at one of the possible core configurations developed for the Brestow 300 reactor plant. The core is assembled from hexagonal fuel assemblies of a shroud design with ribbed rod fuel rods, with the spacing of the fuel rods in the fuel assemblies grid rib by rib. All structural elements of the fuel assemblies, including fuel rod claddings, are made of radiation and corrosion-resistant steel of the ferritic martensitic class. For radial equalization of power distribution and coolant heating, the core is made in the form of two radial zones, central, orange, and peripheral, blue, differing in the design of fuel assemblies. The only difference is that with the same fuel composition, number and spacing of fuel elements with a smaller diameter are installed in the fuel assemblies in the central zone, and with a large diameter in the peripheral zone. In this case, the relative pitch of fuel elements in fuel assemblies in the central zone is 8% higher than in fuel assemblies in the peripheral zone. The developers of the Brest project note that, unlike the known equalization methods by using fuel of different composition or different density in the radial zones, the equalization method using fuel rods of different diameters is more universal. It is also suitable for a promising core made of fuel assemblies of a non-shell design, since it allows equalizing both the power of the fuel assemblies and the heating of the coolant in them. The use of fuel of the same composition in all fuel assemblies, subject to a breeding ratio of about 1, ensures the stability of capacities and heatings over the campaign. Given the reduced thermal power of the presented reactor, 135 MW versus 700 MW in the Brest reactor, partial refueling of the core can be carried out no more than every 5 years, and after a certain time, the reactor can switch to its own regenerated fuel, in which fission products are replaced by approximately the same amount of uranium-238. Of course, this is an idealized picture of the reactor fuel cycle, and technical solutions for fuel reprocessing, as well as solutions to problems with nitride fuel, are at an early stage of development. In addition to the need to solve the problem of the performance of structural materials, there is also the problem of maintaining the oxygen potential in a given range in order to ensure the performance and corrosion resistance of fuel rods. And yet, despite the presence of very serious problems, their possible solution allows us to hope for the creation of an explosion-proof and economical reactor, albeit of a small power. Another important element in the presented concept of the reactor plant is the steam generator, and its parameters can also be implemented in the already developed design of the steam generator for the Brest reactor with a thermal power of 90 MW. As part of the development of this steam generator, the impossibility of the development of a single rupture of tubes into a multiple is experimentally substantiated. The heat transfer coefficients for lead coolant conditions are determined. Verification of the numerical model of the heat insulating gap was carried out on the created working area. The boundaries of thermal hydraulic stability and starting modes without throttling are determined. Steam generator tubes made of a new material were put into production. For the first time in Russia, tubes with a length of more than 35 meters were obtained. Thus, for the main elements of the presented reactor facility, they are already very serious developments within the framework of the Brest 300 project, both in terms of computational and experimental studies. The fundamental approaches of natural safety used make it possible to meet the requirements of competitiveness, including when scaling. Summary: it is proposed to add passive heat removal from the core according to the principle of natural circulation in all operating modes to the numerous advantages of the principles of designing the Brest 300 experimental demonstration fast neutron reactor facility, which ensures the utmost simplicity of the primary circuit without the presence of fittings and circulation pumps. The proposed concept of the underground location of the reactor, along with simplifying and increasing the reliability of the heat removal system, allows solving many problems related to the protection of the reactor from external influences, the duration of the fuel company, the qualifications of personnel, the cost of dismantling the installation after the end of the resource, ensuring the safety of the population in any emergency situations, reproduction fuel, etc. Despite the large number of serious problems that need to be solved within the framework of the proposed concept, the potential gain from the use of such reactors will contribute to overcoming the crisis in the nuclear industry and the development of small modular reactors on a new technological platform. In conclusion, I must express my gratitude and deep appreciation to you for your patience, thanks to which you were still able to listen to this mechanical speech of machine translation. That is it. Thank you for listening.